Any questions before I begin? All right, so let's start out with an insulator with uniform charge distribution. If I'm out, I guess, spherical insulator. If I'm outside the sphere, I can treat it like a point charge, and I just use define the electric field from this, KQ over R squared. So let's give it a radius of the R. So if the distance to a point in question, if R is greater than R, the electric field KQ over R squared. And I guess uniform charge distribution with total charge. All right. Or for the more sophisticated, 1 over 4 pi epsilon sub naught, Q over little r squared, r hat. So if Q ends up being a negative number, then nothing changes in the formula, just a negative shows up, which means it's pointing towards it. And if Q is a positive number, then the direction would be the positive r hat direction or away. But what I want us to look at is what is the electric field at this point, where R is less than big R. So I'm just going to create a Gaussian surface right there of that radius. And again, the Gaussian surface doesn't have to be real. It's a virtual surface that I'm creating. And I know that the electric flux through that is equal to the enclosed charge divided by epsilon sub naught. Well, technically it'd be Q over epsilon, but let's just assume that the permittivity of this material is approximately equal to that of free space. If the insulator were made of paper, then epsilon would be twice that of epsilon sub naught and so forth. I mean, it really depends on what it is, but I don't want to quibble over that quite yet. So how do we figure out the charge that's enclosed? Oh, just phi sub e times epsilon naught? Oh, a true statement. I was looking more for in relative to big Q right here. What is the Q inside that Gaussian surface relative with respect to the total charge? Enrique, is the camera just in your way? You look like you're trying to look around it.
It's fine.
Okay. Well, first off, it's an insulator, so what is that telling you about the charge?
It's not flowing either, so it's going to be at one location.
It's not moving.
Yeah.
Okay, not moving, all right. So if this were a conductor, you would automatically know all the charges on the surface, in which case, what would be the electric field inside? Correct? Since none of you were looking at him, he made this gesture. I assume it was not a crude gesture. So electric field inside a conductor is 0. But this is an insulator, so I don't want the charges moving. So what do we know about the charge distribution?
It's uniform throughout the sphere.
Yeah. So I know that my charge density, which is charge divided by volume, is constant throughout the whole thing. So for the entire insulator, it's cubed over 4/3 pi big R cubed. And for the small one, it's whatever's inside that thing over 4/3 pi little r cubed. Or pi, that 4/3 pi cancels out. And so I'm left with, like, enclosed charge is just the overall charge times little r cubed over big R cubed. I know my electric flux is equal to the electric field times the area. And since my electric field, because of symmetry, is going to be the same magnitude throughout, no matter where I am on the surface of my Gaussian sphere, as well as the area vector is always pointing away, that this just becomes the magnitude of my electric field times the surface area of my Gaussian surface, which is 4 pi little r squared. And that's going to be equal to my enclosed charge, which is big Q times little r cubed over big R cubed over epsilon sub naught. Which, let's get rid of a fraction bar there, so that's big Q times little r cubed over epsilon sub naught big R cubed. We can, if we're looking for the magnitude of the electric field, that's going to be equal, well, we just divide by the 4 pi little r squared, and we end up with Q over 4 pi epsilon sub naught big R cubed times R little r. Because the little r squared cancels out with 2 of the r's that I have on the right hand side. So I have a linear relationship here. Now we can think through the direction. Oh, sorry, Joseph?
Trying to figure this out. How did you change the division of R3 over B naught to multiplication?
So how do I get from here to here?
Yeah, just the bottom half.
Okay. So I have Q R cubed over big R cubed. That whole thing is divided by epsilon sub naught. In other words, divided by epsilon sub naught.
Oh.
Dividing, same as multiplying times the reciprocal. That's how.
Okay. Okay, I was just a little bit confused.
Not a problem. Other questions up to here? Because I think we're about to lose faith. Looks like you're about to fall asleep. Of course, I mean, why would you fall asleep in physics? So my electric field, well, what is going to be the direction of my electric field?
Depends on the charge of Q.
Let's assume positive unless otherwise noted.
So it's going outside the sphere.
Okay, so we end up with big Q over 4 pi epsilon sub naught. So we got this 1 over 4 pi epsilon sub naught, which is just Coulomb's constant, times big R cubed R hat. So outside the sphere, the relationship is a 1 over R squared relationship, but once you get inside the sphere, it's directly proportional to the distance, which would give us an electric field in the middle of 0, which makes sense that you have charges surrounding it, and the electric field created from a charge would be countered by 1 on the opposite side. And so if this is my insulated sphere here, R and E. a 1/r² relationship until you get to the radius itself. So, I'm sure your notes will be drawn better. And then once you get to here, it's a linear relationship. Now, I could have just given you that graph right there, and I said, is this an insulator or conductor? And hopefully you recognize it's an insulator. Because what would if this were a conductor, and I did my plot of my electric field versus R, what would it look like?
The same thing, except when it hits the radius, it just drops to 0.
So we got the 1/r² relationship, and then at this point, it just drops out. So, insulator, conductor. Questions there? About to do one last exploitation of Gauss's law, and then we will talk about when the assessment is for chapter 25, and then move on to 26. Yeah, that's not the way I want to word it. So I want, actually, let's make that nanocoulombs. Sphere of radius 25 meters. Hollow spherical hole. Spherical hole. Radius 0.3 meters. -4 nanocoulomb charge in middle. All right, so I have a conducting sphere, and yes, you can nitpick whether it's a sphere if it's got a hollow core to it, but it's solid. Basically it's a thick-shelled sphere. That's probably better wording. It's got that hollow ball in the middle, or the hollowed out hole in the middle with a smaller radius. Obviously, it's not a TARDIS. And the conductor, the shaded part there, has an excess charge of +3 nanocoulombs. And the question is, what is the electric field at this following radii, or distances from the center? So at R is equal to 0.1, R is equal to 0.4, R equals 0.6 meters. So we will use Gauss's law. I mean, there are other ways of approaching it, but since this is the Gauss's law chapter, we'll sort of work on with that. So at 0.1 meters, so we're talking here, put a little Gaussian surface there. Not to scale. Whatever it is, I know it's inside the hollow area because 0.1 is less than 0.3. I have done tests where I've accidentally left the decimal point off, suddenly making it, for some reason, students not answering the question that I wanted to ask. Thereby showing their mind reading skills being just absolutely horrible. So again, I've got my electric flux is equal to 4 pi, wrong unit system, is equal to my enclosed charge over epsilon sub naught. This is my electric field, magnitude of my electric field times 4 pi r cubed is equal to my enclosed charge over epsilon sub naught. Well, what's my enclosed charge for my first radii? Oh, go ahead and handle this 1, 2, and 3. Hopefully to make communication a little bit more, a little bit easier. So what's the enclosed charge at r is equal to r sub 1?
Why is it 4 pi r cubed?
Because I decided to change the rules of mathematics. Thank you.
Because pi is not square, it's round.
Isn't there some pizza places that do their pie square, the Little Caesars?
Oh.
Or,
You can order it like that, I mean.
there was some place that was their, one of their shticks was that they served square pizzas or rectangular.
Yeah, I can't remember.
How,
They have one of those Caesars, the little personal deep dish one.
Yeah, and then like, you can always order, at the Italian places where they call the really thick ones.
you remember Bill's Pizza?
No.
Okay.
I know the national chains, and then there was a place in Durham that sold really cheap edible pizza. That we called bats because supposedly the owner was crazy, but that was cheap and worth the price. And then they dared close sometime 20 years after I graduated. What's up with that? So anyway, what's the enclosed charge?
Maybe 0. Since the actual charge, there's like, it's an empty sphere there.
I've got this -4 nanocoulomb charge in the middle. So what's the charge enclosed?
-4 nanocoulomb.
There we go. We can just edit that out and it'll all be brilliant. So I got -4 nanocoulombs divided by epsilon sub naught. And so the magnitude of my electric field is going to be -4 nanocoulombs over 4 pi times epsilon sub naught, which is 8.85 times 10 to the -12, times r1 squared, which is 0.1 squared. And if someone would be kind enough,
I got -3,596,
3,900.
3,596.
Units?
The, newtons per coulomb, but I had 359.6. Newtons per coulomb.
Do you put a different exponent in?
Oh, I missed the square.
All right, so it's looking
Yeah.
3596. All right.
Yeah.
Now, from a math point of view, and actually if I asked you what's the magnitude of the electric field, I would actually take off a point for this answer. What's wrong with this answer?
It's negative.
The magnitude technically is positive. I left the negative in there just to sort of remind us that that negative sign is a directional thing. The final answer, if I ask for what is the electric field, there is a negative R hat there, so 3596 newtons per coulomb. And of course, I did not give myself enough room. 3596 newtons per coulomb R hat. The electric field is pointing inwards at that point. Now, what about the electric field at 0.4 meters? So we are now here. And that's a lot of dots. Let's see if I can put it into stunning visual effects. Ooh. How would you find the electric field there?
Is that one 0 because you're inside the conductor?
It is indeed. So if the electric field is 0 at this point, so the electric field of R2, 0, what does that tell you? There's an implication for the fact